I run research over at SentinelOne. All right. Okay, fair enough. So, hello everyone. Just show of hands, how many people are like reverse engineers in the room or have experience doing some RE? Okay, so we'll try to like take it slow, but there's a lot of stuff that we want to cover and like just make sure that we bring folks along. So really quickly, for those of you who have done some RE, you might be more familiar with the fact that like it used to be really hard to reverse engineer things like C++, Delphi, mostly edge cases. And you would say, okay, there's all this garbage that's just sort of thrown into these binaries. The way they're structured is hard. And it was just very difficult for our tools to function the way that we needed them. But I think in large part we were going about it very wrong. I think there's this mentality, this kind of like macho thing that, you know, hardcore reversers stare at the disassembly, they don't bother with the decompilation. F5 reversing is treated as like a thing for, you know, for softer folks. But the truth is that that's a really great way to look at things right until you reach multiple layers of abstraction. At that point, that's exactly what decompilers are for, right? You need something that's going to allow you to model that same level of abstraction so that you can start to try to bring back all the things that you lost during the compilation process. So when we're looking at these new languages, I think we need decompilers now more than we ever have. And for folks who can afford them or have had them on hand, it's almost ridiculous that we haven't been using them as much as we could have. Things are going from bad to worse, right? Before we worried about Delphi and C++, now you have a million ridiculous languages. Every single day somebody comes up with some new amazing side project they decide is the way that we should program. And the truth is that most of these new programming languages suck for us. I'm sure they're having a wonderful time developing in those things, but most of them, you know, have these massive binaries. They have a ton of statically linked code, these like statically linked libraries within the binaries. You have all kinds of different binary structures that people decide to change overnight, unconventional calling conventions, and these like big active development communities that will just make changes arbitrarily. On a Tuesday, they decided that they wanted to just change how the linker works. So you go, okay, well, here we go. The truth is that this is hard because our tools suck even more than those languages, right? So there's tons of limitations. You have all sorts of issues with type reconstruction, complex function prototypes. It's just really hard to like trace how arguments get moved around. None of our tools seem to manage multiple return values. So for any of you that deal with Go and Rust and some versions, you have this issue where you just cannot model the fact that you're returning multiple values. They can't manage recognition of strings that are not exactly what you would expect from your usual C literal. They don't have a good time recognizing statically linked library code. You don't have a good time recovering structures, classes, methods. All of these abstractions, they're just very hard for our tools to manage. And most of the time, everything is just broken, right? If any of you have ever written any scripts for IDA Pro, how long did those last before they just started disintegrating into the wind? So the problem that we really get is when no one is looking at these new ecosystems, you get all of this malicious development, all this malware that starts to come around using these new languages that none of us want to look at because we have a really hard time reversing them. So this is what happened with Go. I think there was a good year or two where people just did not want to look at Golang reversing at all. And it turns out that during that time, you had multiple APTs, multiple ransomware groups, and all kinds of e-crime garbage that started being developed in Go and worked really well. And in the meantime, none of us wanted to look at it. There is some semblance of hope, though, at least when it comes to Go. So I'll talk about this case study relatively quickly because I want us to get the focus more on Rust. But just so that you have an idea, when we talk about Go, why did reversing Go suck so much at the time? Well, portability meant that they had a ton of statically linked dependencies. You can't manage the multiple return values, like we said, complex types, type recovery. The user-generated code was completely lost, right? You had like 40,000 functions, and in reality, there was maybe 10 that had been written by a user. The rest was statically linked code, and you couldn't find them. Stripping binaries meant that you lost information. You couldn't the stack would get reinterpreted, and IDA would actually break. Like to this day, you can break IDA by just trying to decompile an entire Go binary. It'll keep trying to figure out what the stack is with every function call and crash. To this day, IDA 9 included. I'm assuming none of you have IDA 9. I don't have IDA 9. No one has IDA 9. We tried the beta. It's still broken. Anyways, at the time, we came up with this thing called AlphaGolang. That's available. It's on GitHub. You guys can use it. I'm going to breeze through it because I've already talked about it at Recon and a couple of other places. But the idea was we wanted to tackle this issue with Go in two different approaches. First, because I know that IDA Python scripts would break easily and all the time predictably, we just kind of made it a bunch of little scripts. So you could basically take it in steps and say, I'm going to try this, then this, and this. Worst case scenario, one of my scripts breaks, but you can still do what you need to do. It's not like these big monolithic tools. And the other thing was really to consider this as a step-by-step methodology, because the issue that we have is not that Go is hard to reverse, it's that our tools can't find all of the information that's readily available in these binaries and surface them up to the analysts so that analysts can reverse that stuff. So the methodology was basically how many steps can we go through where we bring back information that analysts need to see, and then you can go and reverse engineer Go, and it turns out it's not as hard as you might have thought. So we're going to walk you through this one really quickly, again, because I'd rather we focus on Rust. But just so you have an idea of what the project was at the time, wrote a Yara rule so that you could identify Go binaries. Then it turns out that the PCLN table, which includes all the symbols for what function is connected to what name, doesn't disappear when you strip a Go binary. They just remove the headers. So we came up with a heuristic where you could recreate that table, that segment, and this actually works in IDA 6.8. So for those of you that are still, back in the prehistoric ages, it'll still work. It meant that we could rediscover all missing functions and restore all of the original function names. So right there and then, it's a delightful exercise for those of us that are trying to reverse engineer. It's why I actually, post AlphaGolang, I tell people reversing Go is actually easier than reversing most other things if you've put the information back in place. Then, once you've already recovered everything, you can actually resurface all of the user-generated functions. So if you watch this kind of closely, you go from several thousand functions that you wouldn't know what to reverse to, oh, actually, the only things written by a human being involved in this malware are those, like, let's say, 15, 20 functions. Then we can fix all the string references. This one's a little janky. But essentially, because this is not C, the way that Go structures the strings in a binary, they're laid out by increasing order of size. There's no zero delimitation at the end of the string. That's why IDA or most reversing platforms will just give you a block of text every time you look at a string. It's because it doesn't know where it ends. But that doesn't mean that we can't tell where it ends. So you can fix all those, and then you can actually extract type information. This is a script that Ivan, I can't say his last name, Kwiatkowski, contributed, where you can recover some of the type stuff. The result at the end of the day is when one of the Russian wipers that was hitting Ukraine early on was actually written in Go, Desert Blade, we loaded it up, we ran through all the steps of AlphaGolang, and we went from 2,400 functions in need of reversing with no names, etc., to 8 user-generated functions. Easier than C, easier than most things that you're ever going to reverse. We just need to put all the stuff back in place before an analyst has to deal with it. I'll leave the hard stuff to Nicole.
All right. So we were thinking that with Rust, we'll have like the same success. Naive. So the first version of Rust was released in 2015, and in 2016, the first Linux backdoor written in Rust was published. So threat actors picked it up really fast. What is so special about Rust? It's cross-compiled language, very strict compiler that is very capable. It can detect memory issues before the compilation. So it is much safer and supposed to be even faster than C. It has cargo, which is the dependency manager, also very capable, and we can compile with using cargo. It is actively developed. There are new tools, new libraries, new code every day. Every night there is a new version of Rust, so you can see how it makes this whole infrastructure much more bigger and harder to reverse. When we look at binaries that were compiled using Rust, we're looking at huge binaries with so many strings, but none of them are the interesting strings because usually they're encrypted. We look at huge functions, thousands of functions with no clear calling convention, lots of stack variables. In the decompilation, things get very messy. We'll look at it in a second. So we also understand why threat actors would choose Rust, because it is so hard to reverse, and the malware is more efficient. And we see new malware being developed in Rust, for example, Rust Bucket, and we see how malware that was previously written in C or even in Go is rewritten in Rust. And it is widely used by nation states, e-crime, ransomware, and basically we see Rust more and more. But why we're not reversing Rust, right? Why is it so hard? Why we don't have tools? And the truth is that it is hard. And for the same reason, we're not talking about NIM, Kotlin, or any other stupid language. It is hard, and we don't want to deal with it. So the question is there hope? And there is none. Thank you. So we wanted to give up a few times, I think, but we decided to stick with the project. So where do we start? We want to look at binaries and see what information we can get out of them, before even opening IDA. Looking at strings, looking at structures, sections, and so on. And we can do it for B files, ELF files, and for Mac. And it was a very tedious process because it is hard to compile Rust for the beginning. And then when we open it in IDA, we need to fight with IDA Python, and IDA doesn't work. It was a nightmare. We wanted to quit, become farmers. It was a whole thing. But before we talk about this whole project, we presented it a few months ago in Black Hat, and that's the feedback we got.
This was suggested to us at last night's dinner, and I think it's important that we do some expectation management.
Yeah. So after reading this, we went to do this, eat our emotions.
Wait, sorry, what were those?
AlphaGolang.
AlphaGolang.
But no, for real. So we understand why they said what they said. But the thing is about Rust is that what we thought would work for Go doesn't work for Rust. The tools are broken or worse.
Yeah. Basically, what we're going to keep fighting through this whole process is you're going to see a similar process of trying to get information back and a realization that the decompilers themselves are not handling Rust well. So we're going to keep surfacing the info. We also need people to fix their fucking tools, and we can't do that part. So just to manage the expectations as we go forward.
And one more thing, the community. So we started this project, but we never intended to be the only ones who figured Rust out. We want to use the community. We have actually a community of other researchers that are trying to fix same issues with different tools, different platforms. So our intention is to share the knowledge and to work together. So how messed up Rust is, this is like a very simple code, 15 lines, that many megabytes.
Yes.
And then when we open IDA and we try to decompile it, we have like the disassembly, which kind of makes sense. And then the decompilation is like, whatever.
Yeah.
And then, yeah, we're going to use memes. And then whatever this is.
That was supposed to be a function prototype with like 40 arguments, I suppose.
So yeah, it was fun. But no, for real. We want to try to fix things, and we will start with, as Jack said, step by step. First, we want to identify Rust binaries. We made the Yara rule for that. It was easy. Then we want to see what information is available, and we begin with strings. So we have both stripped and not stripped binaries, and for both of them we have the Rust version, and what you can see there is basically the commit hash. So for each binary we can know exactly which Rust version was used. And there is a way to strip even this information, but we didn't see it in the wild yet. Then cargo, the dependency manager, leaves also bunch of paths of the libraries that were used. So we can extract those and know at least which dependencies are in the binary. Identifying these functions, that's a different story. Next, we want to create structures because the functions are so big and it is so confusing. We want to see what information we can build into some sort of a structure. And the first thing we want to do is look at strings. So in Rust, we have strings and we have slices. Basically, a slice has the content and the length, and the strings has also something that is called capacity, because you can change the string, you can append more data into it. So we defined structures for that, and we add them to IDA. So strings, slices for 32 and 64-bit. Now, if we look at this very simple code, with some slices, what we can see is that basically we have the content in our data and the length in the text section. So it is a bit messy. Then if we go back to our data, we have even more strings. Some of them are basically the paths from the cargo dependency manager, what we have extracted in the previous section. Now, if we look at strings and we have immutable and mutable strings, it becomes a bit worse. And you can see that the strings are reversed, though they silently fixed it now.
Yeah, we've been fighting with the hex race folks where we suggest things they can fix, they don't tell us, they fix them quietly, then they don't fix other things. So depending on what version you're in, you will have to deal with this part, where it's like the first 16 bytes of a string will be stored in an XMM word, so IDA reverses it, and then the remainder of the string, it's in the normal sense. So
Spoilers.
We wrote you a little script to fix it, right?
Maybe it will work.
You were drinking water, it's fine.
So yeah, for longer strings, as Jack said, we have memcopy, and then we have XMM words. And you can see the mess. It's both in the text section, in the Pdata, and then the compilation is fucked.
It's a technical term.
Yes. So we wrote a script that knows how to identify both slices and strings, apply the structures that we presented a few slides ago, and make it a bit nicer. And just one thing about Rust is that right now it looks nice, but if the function is longer, we'll see the same variables being used in different functions or different calls. So it is all messed up again. So basically, the issue with slices is that they're in different sections. We're trying to fix it, and okay. So the next thing is the Pdata. So for binaries compiled with cargo for Windows, we noticed that there is a bunch of information in Pdata, and specifically our functions. and other things. So we tried to parse it and see what we get. And what we learned is that symbols in Rust are organized in a very specific way in this Pdata section. Basically, each model or library will have these functions in the Pdata. And then we'll see the traits implemented and then the functions for each type. So there is some way to organize and parse this information. And what else we noticed is that these functions in Pdata are the only functions that have some sort of exception handling. And that's why we see so many library functions in there. But usually malware developers would not implement exception handling, so we will not see user-defined functions in Pdata. And that allows us to create some sort of organizing the functions. So we can say, hey, all of these functions are in Pdata. Most of them will be library functions. The rest of them are different functions. Some of them are the user-defined functions. So instead of looking at thousands of functions, we have about 10 or more, which is much more manageable. And one more thing about the Pdata section. Whenever an exception happened, the runtime needs to understand how to handle the stack, how to unload functions, and what to do next. And in Windows files, there is a structure called unwind, and it has all the information about each function. So when an exception occurs, the runtime will know how to handle it. So this information is in Pdata. So we start to parse it and to show it. We actually had to fix the structure in IDA, by the way. But once we did it, we present this information. Now, right now, you might say, what is the point? Like, how does it help us? Well, we don't know yet. But we have this information. We have a bunch of binary files. We can start to analyze it. And we hope that when we have enough information, we can start to use this information maybe to identify these symbols and use them in strict binaries. Or maybe we'll have another idea. Maybe the community will have another idea. But that's part of the project, to find information, parse it correctly, and present it. And then we will see how we can use it. Maybe we can use it to identify the calling conventions, because Rust supports all the calling conventions. So maybe we can use it.
So a note on the calling convention bit and why it bothers us so much, since some of you are not as experienced reversers. A calling convention is what tells you in what order the arguments are being passed into a function. So when you have this wonderful world of Rust where you can just have any of them and custom ones and change them between different functions in the same program, it means that IDA just doesn't know what the hell it's receiving, how many are actually coming in, like how many arguments are coming into the function or what to do with them. So it's part of this disaster. So kind of hoping that information like what Nicole is parsing here will actually help us out, because you go, well, the stack is supposed to be this big, it's supposed to use these registers, maybe we can sort some of it back. Part of the things that are helping us have some hope as to what we can parse out of these is things like, our love of panics. So we kept reverse engineering these different Rust binaries, and we would see these offsets to something. And we really weren't sure what that offset was that was being passed into these functions. And when we looked, there was some kind of structure being defined here with a reference to a string that was a file name of some sort. So we figured out just to define this debug info structure, added it into IDA, and then redefined these. And what it turns out is, because Rust uses macros a lot, when the macro, let's say like a print macro or some other, is being expanded, it actually adds a lot of stuff that normal developers might not care about, like panic information, how to handle some of the stack stuff. And in this particular case, it actually adds the file path, the line number and column number of where this error is being produced from in order to be able to surface it in a panic, which actually means that you have this spotty map of where in the binary these things are connecting to standard code, where we literally have like the version of Rust this comes from, the file that it comes from, the line that it comes from. So when you start to put, as Nicole mentioned, you start to put some of the information back into the binary, it turns out that then, okay, let's move up the stack. What's calling this thing and what is it doing? Now we can identify all of the structured exception handling that is standard in the implementation from Rust, start to name and manage some of that information, and then keep moving our way up. So this is how we start to carve, like, look, it's a mountain, we're carving it with a spoon, but you find some things that are really actually incredibly useful when you get into automation. So we're starting to automate a lot of that stuff. You'll see the scripts at the end, but there's also things that have not been quite so fruitful. One of my previous obsessions was this notion of birefs, which I'll move through very quickly, but essentially you can reference data from variables by reference to where in the stack they are. And in the case of Rust, what we kept seeing were so many biref references to other parts of the stack that it almost felt like function scope was being routinely broken. So the function, anybody who's ever written any kind of code, right? The life of a variable is the scope. If it's a local one, it'll be in that function and that's it. That's not what we're seeing when you're compiling Rust. It seems to be referencing things that are way further back in the call graph. So we started to wonder if this was a way that data was being manipulated that we couldn't see. We were told that maybe we were looking at a use of closures, which is just one of these newfangled programming concepts that I'd rather not go into because I barely understand them. So we were like, oh, maybe this is how like these secret arguments are being passed around and because of closures, or maybe it's just the stack sizes. So we're waiting for IDA improvements, but one other possibility started to arise the more that we played with this, which is that the decompilers are so broken that this may very well be essentially the equivalent of a decompiler hallucination. All the types and sizes are so off that the decompiler just doesn't know where information is being moved in and out. We were hoping, when we engaged in this, that the folks at Hexrays and Ilfak in particular, who was in the crowd at Recon when we gave the talk months ago, would help us out. And they were very kind and they promised to help, but the truth is that I don't think we're going to get the kind of help we need. IDA 9 came out. It's got a lot of fancy, cool improvements around the workflow and things that we've been asking for a while, but the decompiler is not any better with Rust. So that hope kind of went out the window. So what are we working on now? Well, remember the stuff that we surfaced in the beginning, right? We said we can figure out the compiler, the specific compiler version, specific Rust version that you're using, and we can figure out what the dependencies are that are being baked into it, including specific versions of those dependencies. So you can essentially kind of look at the equivalent of this sort of cargo TOML file and actually have this nice little dependency tree. Now, there's the way that we could use this, and then there's the way that IDA, the Hexrays folks, decided to use it. I'll give you a peek of sort of what the Hexrays guys are doing, though this, again, is for the rich and affluent who can get IDA 9. So now they have this Flirt signature manager. The idea is they made signatures for every Rust version and all kinds of different potential things that are compiled into your binaries. And they actually made a way that you can essentially brute force your way through saying, hey, get all the Rust ones, sort of brute force to see which one matches. This one has 58 matches. Let's apply that signature, and all of a sudden you recover a bunch of the functions there. Nice, useful, not complete, not accessible to most people here unless you suddenly get a very expensive IDA license, but it also tells you kind of where we have to go with some of the automation in general, right? Like there's nothing keeping the rest of us from pulling these files, compiling them, building signatures out of them, and applying them. It's just that, who the hell wants to do that? So there's a certain amount of automation that kind of needs to go into play with this. but it helps a lot. So when you fold that stuff back in as IdaPro flirt signatures, you can get a ton of sort of this library stuff, traits, generics, etc., put back. The problem is it requires everything we just talked about, ton of cross-compilation, and it's a very heavy lift. I'm glad they're taking it on. It kind of sounds like we're going to have to take it on as well and just provide it to more folks. But in any case, it's there. So where does that put us now? So far, we've provided pretty much all the things that we've discussed you can have to a certain level of automation with the scripts that are already in GitHub. We've been refactoring the scripts, so I've been kind of breaking them. I'm sorry, but they're available. In the process, I think we kind of ended up birthing something that I think might ultimately be more valuable than what we do for this Rust project, which is another project that we call feature proof. So we were building this right before IDA 9 came out, and we were scared that everything we built was going to break, essentially, within a few months. So we created this thing called feature proof, which is a middleware library. The idea is we abstract, I got the idea from how the equation group people do their malware. You abstract functionality away from the specific implementations of IDA Python, because then you don't have to worry about whether it's version 6.8 or version 8.4 or version 9. And we just give you this sort of abstracted notion of what you want to do. I want a function that gets me the bytes at this address. I want a function that renames this symbol. You don't actually need to know what the specific implementations are. So we've been building the scripts on top of this middleware library. And the reason that I say that it might actually be more useful than this project ultimately is that we're getting some support from the Vector35 guys to also potentially implement it in Binja. Maybe somebody will want to, some masochist will want to implement it for Ghidra. I'm not going to be that person. But in any case, it's how we're abstracting this away in the hopes that this doesn't break. If some of you want to build new scripts, I encourage you to please check it out because I find it particularly useful. So from here, where do we go? This has been a slog. It's been actually really hard to kind of move from piece to piece, but there are already avenues that we can see going forward that are going to provide other types of information. So the unwind info that we discussed for managing stacks and et cetera, exception handling, it's actually very different on Mako and ELF. ELF also includes a certain amount of dwarf information, which usually has a nicer tie-in with symbols. So we need to go implement this more or less, or parse this for each different platform. If any of you are more familiar and want to take that on, that sounds amazing. We also want to figure out what to do with the stack unwinding information. There's a certain amount of double checking we should do, right? Like the decompiler or the disassembler says the stack is yay big. Well, we have information here that says the stack should actually be bigger, etc. So there's different ways where I'm kind of hoping this will lead us closer to establishing what the right calling conventions are, but we're not quite there. There's also a certain amount of work that we should do for type recovery and size mismatching. Particularly for type recovery, there's a ton of generic info that Rust is creating in the form of functions and constructors and destructors that we need to figure out a way to brute force back in. But it's a lot. And then the most important part here is really that the decompilers are broken. And they're broken for Go as well, right? Like looking back at IdaPro and even with all the stuff that we built for AlphaGolang, we're bringing information back to help you, but at no point is your decompilation going to look super pretty unless Hexrays basically rebuilds portions of the microcode and the decompiler for Go and for Rust specifically, which so far they have not done. I hope that they will in the near future. And then, I want to see if feature proof withstands the test of time and actually helps us future-proof our scripts so that we don't have all these issues where somebody wrote a great tool 2 years ago, it's broken, there's another tool, it's broken, the next tool also broken. So let's see. In the end, this was supposed to be a 6-month project that is now a 9-month project that is probably going to turn into at least a year-long project. But our eventual goal is not just to become the most autistic Rust reverse engineers of all time. It's actually to go back and hunt deeper into this malware ecosystem of Rust stuff that's built out there. There's tons of compiled Rust binaries. Nobody is looking at them. I promise you there's tons of cool malware just hiding right there that people just don't want to deal with. The likelier outcome is that we will become farmers and just kind of give up on all this.
No, there is no hope.
There's no hope. I'll leave that to you. I have no hope to share.
But there is hope. So Binary Ninja, the more affordable and maybe our next favorite tool, as hard as it is to say. But basically what we noticed while we were working on this project is that we have the source code again, and then all of a sudden we see this is Binary Ninja, and we see the Rust, the pseudo Rust in Binary Ninja, right? So yeah, we got very excited. But so there is hope with Binary Ninja, but does it help us to do the hunting? No, maybe. It makes it a bit easier, a bit nicer to look at, but we're still not there, not like with malware in C or Go. So we keep working, and one of the things, the next things that we actually want to do is we were able to collect all the Rust binaries with the help of VirusTotal, and maybe we can build some heuristics on top of that and collect more information on this massive database. And hopefully this will be something that will provide better results.
When all else fails, we turn to big data because we can't really figure some of this stuff out. So the VT guys are helping. The tools are up already. I am not like super triumphant in putting them out because we're still refactoring a lot of this stuff. So you'll see a refactoring branch that has more capabilities. But in any case, look, stuff is out there. We'd love some help. We'd love some support. You know, just like the feedback said, we haven't solved the problem for you. We are not going to solve this problem for you. But we hope to get everybody a bit closer. And something that might actually be beneficial to people here, like how many of you have IDA licenses? Like legit IDA licenses? Okay. Binary Ninja costs 1/10 of the price of IDA, and it's working better. I hate to say it, I've been an IDA Pro user my whole life, but I think we're getting to that point where the architecture of the decompilers is just proving to be more flexible, more usable, more future-proof. So Binary Ninja may very well be the solution, and I'm hoping that future-proof will mean that everything we've built here will port over to Binary Ninja with relative ease in the next few months. So with that, I think maybe we have a few minutes. We have 5 minutes. If anybody has questions, please, Nicole will answer all of your questions.
About alfajores.
About alfajores, yeah. Guys? So the question is, what about Ghidra? I personally refuse to use Ghidra because I don't like Java. No, I've been trying to avoid Ghidra just because I can't work with Jython and all this kind of stuff. The way the feature-proof is built, it should accommodate that if somebody wants to implement it. Now, more specifically about Rust is there are folks who have been working on fixing up some of the intermediate microcode for the Ghidra decompiler to try to make it a bit friendlier to Rust. It's still not a better situation. I mean, look, the way that the decompilers are sort of architected right now, IDA Pro has a very specific flavor, which is we're going to manually figure out how to handle an architecture, and then we're going to manually create a decompiler for each for each sort of architecture. With Ghidra and Binary Ninja, it's an intermediate layer of abstraction that stacks until you get to a C pseudocode, which means that anything they can disassemble, they can decompile, in theory. The problem that we're getting to with these new futuristic languages is somewhere when you're getting close to that high-level IL, before the C pseudocode, things go off the rails. Variables are reused, or there's dead store variables, or the sizes are not right, or it doesn't figure out the type, so it just doesn't know what to do. But it means that with the way that it's architected, if you're a huge Ghidra nerd, you could try to fix it. And there's some folks who are trying to manually fix that last step when you get to high-level IL to actually go to C pseudocode. So there's some stuff out there that will help. It's still not perfect. they still hadn't architected for things like multiple return values and stuff. And that's why it's so nice to see this pseudo-C that Binary Ninja's got going on, because they're trying to start adding some of that syntactic sugar and the ability to do it. It's just still not great.
For Ghidra, there is also, they're making the signatures, because it's a different way than IDA. Max from Thrillix,
Yeah.
he's working on creating all these signatures for the dependencies and import them into Ghidra, and I think he having like
Yeah, Max
nice results.
Kirsten is pulling, like he's doing the hard work of like pulling down every version and trying to compile it, build the signatures and put them out. So there's some saints among us. We're gonna have to do that basically for each one of these platforms. Anybody else? Last chances? Favorite alfajores? All right. Thank you, everybody. Appreciate it.